Now we want to look at potential graphs in a more qualitative way. The way to think about these graphs is to think about them sort of like terrain graphs or like a roller coaster, where a positive charge will spontaneously move down the potential graph, and it will require work to push it up a potential graph. In this case, we have a positive point charge placed in the middle of our graph, so the potential increases as you approach that positive charge, and the value is positive, like the charge, right? You have a positive charge, you have a positive potential. The voltage, or the potential, is equal to K times Q over R, so the positive charge will have kind of like a mountain, and it will point up. And if we had a negative charge here, then it will be more like a pit, and it will point down. If we were looking at a uniform electric field, then the potential would be a sloping line, where if the electric field is pointing to the right, then the slope would be negative, and the positive charge would want to roll down the slope to the right. But in our case, we have a positive charge, so that means we put a positive charge to the right of it, and it will roll down the mountain to the right. If we put a positive charge to the left, then it will roll down the mountain to the left. If we have a negative charge, then it will do the opposite. Our negative charge will be attracted towards the positive charge, and if we put a negative charge to the left, then it will be attracted to the positive charge, and it's going to move towards the right. In this case, we don't really need a potential graph. If we know that there is a positive charge, then positive charges will repel and move away from the center charge, and negative charges will be attracted and move towards the positive charge. However, we can plot these graphs in increasingly complicated systems, so it's good to look at a few simple examples to see how they work. So now we have a series of pairs of point charges, and we are asked which one corresponds to two negative charges. Well, when we look at a potential graph, positive charges are like mountains that other positive charges have trouble climbing, while negative charges are like pits that the positive charges easily move into. So which graph here has two pits? Well, it's graph B. In that case, both particles have negative potentials, so if they have negative potentials, then they must be net negative charges. Now we're looking at a positive and a negative charge that are next to each other, and the potential graph is shown. The charge on the left is a positive charge because the potential is positive, and the charge on the right is negative because it has a negative potential. So we are asked, if we place an electron in between the two charges, which way will it go? We can answer this two ways. One way is that a negative charge will roll up a potential curve, so that means that it will move to the left. Remember, the potential tells you the terrain that a positive charge will follow, so it will have to do work to move up, and it will easily move down the potential. But with a negative charge, it's going to move in the opposite direction, and so it's going to move up a potential curve, and it's going to take work to move down a potential curve. Also, once you marked that the charge on the left is positive and the charge on the right is negative, then, well, you can look at the negatively charged electron, and you know that's going to move towards the positive charge, so it's going to move to the left. Either way, you get the same answer, although if we give you a more complex potential graph, then you will need to know how the positive charge will move downhill, and the negative charges will move up the potential curve. In our next case, we have two positive charges, some distance from each other, and we place a positive charge in the middle. If we do this, the positive charge will be stuck in place because the potential increases to both the right and the left. So it is stuck in what is called a local minimum, and our charged particle will stay there, and it's in equilibrium for a long time. The slope of the potential graph corresponds to the negative of the electric field, so the particle, if the particle moves to the right, it will be pushed back to the left, and if the positive particle moves to the left, it's going to be pushed back to the right. On the right graph, we have a positive charge between two negative charges. Here we also have a spot in the potential graph where the slope is zero, so there is no net electric field and no net force. However, in this case, the slightest bump to the left will cause it to move to the left, and the slightest bump to the right will cause it to move to the right. This means it's not in an equilibrium. This is something called a saddle point often, where a positive charge will most likely lie on one side or the other, closer to a negative charge, and then the height of the saddle point is how much potential is needed to be overcome to jump from one negative charge to the other. So yes, there is a spot in the middle with no slope and hence no electric field and no electrostatic force. But this is a very different situation where any perturbation will knock that positive charge out of place. Notice if this was a negative charge, then we would be in equilibrium again. Our negative charge would now be in a local minimum, and if it moved to the left, it would be pushed back to the right. If it moved to the right, it would be pushed back to the left. All right, I think this is enough material for this week. Next week, we'll have one more day on electric potential and looking at things like electropotential surfaces and what happens when we have more complicated systems. And after that, I think we'll get to start to do circuits for our Thursday's class next week. All right, don't forget you have classwork to finish for Friday morning, and you have a homework due on Monday at 10 a.m., so good luck and take care of yourselves.